Okay, don't get thrown off by wording here. You've got sodium sulfate. Sodium is +1, sulfate is -2, and so the formula is Na2SO4. This is going to break into ions and produce 2 NAs and 1 SO4 -2. So you don't need the milliliters at all. Okay, we're just talking concentration. So if the concentration of sodium sulfate is 2.104, then sodium, it's a 1 to 2 ratio. There's twice as much sodium. It breaks into 2 pieces of sodium. So you just double this and you get 4.208. And the sulfate, it's a 1-to-1 ratio. Every 1 mole of sodium sulfate breaks into 1 mole of sulfate ions. And so you have 2.104 molar for that. Question 2, your answer is 1.67 for the molarity. Let's see how to get that. Remember that molarity is moles of solute divided by liters. So if you take your 0.500 moles and divide it by 0.300 liters, you get 1.67 for the molarity. 3. Aqueous potassium chloride will react with which one of the following? It's going to be lead nitrate. That's because lead and chloride make an insoluble precipitate. First of all, potassium will not make any precipitates with these guys. And so what you're looking for is calcium chloride soluble, is sodium chloride soluble, lead, barium. Which one is insoluble? And lead is insoluble, so lead nitrate will react with potassium chloride. Question 4, it's A, and this is just a solubility rule thing. You check out your solubility rules, we see that for the most part, insoluble ionic compounds, phosphate is insoluble. There are some exceptions. Alkali metals are the first column of the periodic table. Magnesium's in the second column. So magnesium phosphate, we would expect it to be insoluble. 5 is A. This is very similar to question 3. You need to know which one of these will make an insoluble precipitate. And nickel and silver swap partners. Silver bromide is insoluble. Again, you can check out your precipitates right here. These are soluble ionic compounds, so bromides are almost always soluble. There are 3 notable exceptions, including the silver. 6. 6 is kind of tough. It's D, a molecular compound and a strong electrolyte. The reason that is, okay, let's say you don't even know chloric acid. Strontium hydroxide, you got SrOH2. Sr is +2, hydroxide is -1. Chloric acid is HClO3. But even if you don't know the ClO3 part, that's irrelevant. I'll show you why. This is going to react in a single replacement reaction. Remember, you've got a base and an acid, so you're going to get H is going to bond with OH, so you get water, and you get Sr bonding to ClO3. Okay, now again, let's say you didn't know what chloric acid is. You know it starts with H, but you don't know what this part is. It doesn't matter. This part doesn't matter. What you've got here, you've got a base and an acid. It makes water. Water is a molecular compound, a non-electrolyte. Molecular just means covalent. So you got a molecular compound, a strong electrolyte, a metal, and an ion. So that would be a strong electrolyte. It's ionic, it's got a metal in it, and that's why D is the best choice. 7, you have a list of strong acids. Your strong acids are on this list right here, and HF is not there. So we would go ahead and pick D for that one. Number 8, we've got B for this. Okay, which one does the oxidation number of hydrogen change? Well, here hydrogen's +1 when bonded to a nonmetal, and here it's 0 when it's all by itself. So it goes from +1 to 0 there. Hydrogen is not changing in that one. A real quick way of looking at this, whenever you've got something by itself, you know it's 0, and when it's bonded, you know it's not 0. So that's a real telltale sign that an oxidation state is changing. 9 is C. Which of these metals will be oxidized by ions of cobalt? Well, for that, you just look at your activity series here. Here's cobalt right here. Anything above it, iron is above it. Iron wants to be oxidized more than cobalt does. And so, which metal will be oxidized by cobalt? Iron will. Iron wants to be oxidized. This is like saying Fe, metal, plus cobalt ions, I don't know, you can just call it +2 if you want, it doesn't matter what the charge is, will give you iron ions, maybe what, +3, and cobalt metal. Again, don't worry about the charges. But what happens here, will iron become positive more than cobalt will? Yes, according to the activity series, iron is more likely to become positive than cobalt. Okay, the ease of oxidation increases, the ease of becoming positive. So, iron gets oxidized, iron becomes positive when there's ions of cobalt around. All right, number 10 is C. A 0.2 molar solution is produced by this right here. Okay, how do you know? Well, you can take 0.02 liters times 5 molar to give you 500 milliliters of 0.2 molar. Okay, for number 10, it's C. And to do that, just use your dilution equation. M1V1 equals M2V2. And you want your final molarity to be 0.2. So we're saying 0.2 is final molarity. And this works when you plug it in. 20 milliliters, that's your volume 1. 20 milliliters. 5 is your beginning molarity. And you want the final to be 500 milliliters, so we do that. Does that math work? Does 500 times 0.2 equal 5 times 20? And it does. So because the numbers work out, it's C. 11. The concentrations, you've got 0.2 moles of FeI3, and what you need to do is remember that FeI3 breaks up into iron ions and 3 iodide ions. And you want to get the moles. Okay, get the moles. You got 0.2 moles of this in 0.725 molar solution, or I'm sorry, 0.725 liters of solution. So one thing you can do is just take your 0.2 moles, divide by 0.725 liters, and that gives you 0.276 for the molarity. So the molarity here is 0.276. It's a 1-to-1 ratio. You can get your molarity of iron. It's just the same, 0.276. The molarity here is 3 times the molarity of FeI3. So just triple this to get the iodine molarity. 0.276 times 3 turns out to be 0.828 molar. So 0.828 molar for iodide, 0.276 for the iron. 12. What volume must be diluted? This is a dilution equation. Okay, dilution, just do M1V1 equals M2V2. And M1 is 6. We don't know what V1 is. M2 is 1.5, right there. And V2 is 200 milliliters. Divide both sides by 6. And we've got volume 1 equal to 50.0 milliliters. 13, what mass of potassium chloride? It's 6.19. Let's see how to do that. You've got 430 milliliters of potassium chloride solution, has a chloride ion concentration of 0.193 molar. So first of all, potassium chloride just breaks up into potassium and chloride. Okay, so the 0.193 molar for the chloride ion, that's also 0.193 molar. It's a 1-to-1 ratio. It's 0.193 molar for the KCl as well. So once you know you've got molarity is moles per liter, plug in your molarity. Your molarity is 0.193 for the potassium chloride. Your moles, we don't know yet, but we know the volume is 0.430 liters. You gotta have liters and molarity. Multiply these together to get your moles. 0.083. Then you convert to grams. Take 0.083 and multiply by the molar mass. KCl, add up K plus Cl on the periodic table, it's about 74.6. Multiply that out and you get 6.19 grams. What mass of calcium fluoride is formed when 47.8 milliliters of this stuff is treated with an excess of aqueous calcium nitrate? It's going to be 0.623 grams. Let's see how to do that. All right, first step is to write the balanced equation. Now, because it's saying that CaF2 is formed, we can assume that that's our precipitate. So we're going to take calcium nitrate. We've got excess calcium nitrate, it says, and NaF. And we make CaF2, and the other product is NaNO3. Balancing the equation, we're going to put a 2 right there and a 2 right there. Now the question wants to know how many grams of calcium fluoride do we get? Well, we are using molarity in liters. We can change this milliliters, change that to liters, and we can get our moles by taking molarity, molarity times liters, and that's 0.334 times 0.0478 liters. That turns out to be 0.01597. That is the moles, okay, the liters times the molarity, that's the moles of NaF. Now it's a 2-to-1 ratio. Right, 1 mole of this for 2 moles of sodium fluoride. So we take this times a half. We do that, we get 0.00798 moles. Calcium plus 2 fluorines. Add that up from the periodic table, we get 78.1 grams per mole. Take our moles, multiply by our grams per moles, and we get our grams of 0.6, I'm not going to write it, yeah, I'll write 0.623 grams. Now it also says to write the balanced net ionic equation. What are the spectators here? This is our solid. That's our grams of solid. Everything else is aqueous. So the net ionic equation is this right here. These are AQ and AQ. Okay. With this last question, we can write the equation. We've got PbNO3 2 reacting with 2 NaCl's, and that will give us PbCl2 and 2 NaNO3s. All right, we need to get the moles of the lead nitrate and the moles of the sodium chloride. And then we're going to compare them to see which one is the limiting reactant. So to get the moles, we take our liters times molarity. So first with the lead nitrate, take 0.250 liters, multiply by 0.15 molarity. 0.250 liters times 0.15 molar gives us 0.0375 moles. That is the moles of lead nitrate. Similarly, we're going to take our liters, 0.300 liters, times the molarity, 0.20 molar. That is the molarity of NaCl. And that, when we multiply it, gives us 0.06 moles. Now, given the 2-to-1 ratio, we can figure out which one is the limiting reactant. And the limiting reactant is sodium chloride. How do we know that? Well, look at this. You need twice as much sodium chloride as lead nitrate. So take this times 2. You get like 0.075. We have only 0.06. We do not have twice as much sodium chloride as lead nitrate. So we have too much of this. This is excess. This is limiting. So we're going to use this. The question says, what mass of precipitate? Our precipitate is lead chloride. Everything else, this was aqueous, aqueous, aqueous. Lead chloride is our precipitate, and it's a 1-to-2 ratio. So you use the 0.06 to get the moles of lead chloride. 0.06 times 1/2 is 0.03. Now on the periodic table, look up Pb and add 2 chlorides to that, and you'll see that the molar mass is 278.2 grams per mole. If you take 0.03 moles, multiply by 278.2 grams per mole, you will get the mass. And the mass turns out, I'm just going to write it down here, the mass turns out to be 8.35 grams. Again, that is by multiplying 0.03 and 278.2. So that is the grams of precipitate that will form. Lastly, we write the balanced net ionic equation, PbCl2, that is our only precipitate. Okay, PbCl2, and where did that come from? That came from Pb aqueous and 2 Cl's aqueous. All right, that's the net ionic equation.